Perfect. Thank you very much. So my name is Carolina, and I'm a PhD student at Durham University, where I've been working with this really cool group of people, the Forge collaboration, on using n-body simulations to constrain theories of gravity other than general relativity. So let me first go to the main idea. So what we want to do is start with any gravitational action that defines the theory of gravity and use data from the large-scale structure of the universe to constrain it. So in the future, that will be probably DESI and Euclid. And the thing is that these data sets are going to have really unprecedented degrees of precision. So we really need to have theoretical models that can deal with that. And especially, we really want to extract all the information that really is about the theory of gravity. We're going to have to worry about what happens outside of the linear regime. And to do that, perturbation theory is not going to be good enough. We're going to have to run n-body simulations. So what we want to do is start with a set of the order of 50 n-body simulations for each one of the models that we want to test at varying parameter values. So we'll vary both the cosmological parameter values and the parameters of the theory of gravity together, because they might be degenerate, right? So if you really want to have robust inference, you need to worry about them both. The idea is that we will combine these n-body simulations with the data to produce likelihood estimates that will allow us to get the posterior for both the cosmological parameters. You can see here an example for the FFR theory, in which you have omega matter and sigma 8 and constraints on the modified gravity parameter. So that's the main idea. In this particular talk, I'll be looking at two examples. So there'll be two models of gravity that we'll consider. One would be FFR. So you can see here the action for that theory is very similar to Einstein-Hilbert action, but we have this plus FFR term. So this is a function of the Ricci scalar that in the end acts like a scalar field, and that will mediate a field force. So the phenomenology of this model is very interesting because you have another additional gravitational force on top of Newtonian gravity. We will also look at the Entp model. So this is a 5-dimensional model in which you have the matter, so basically the standard model particles living in a 4-dimensional brane, which is embedded within a 5th-dimensional spacetime. So in this case, you can see how there's a free parameter RC that will control how strong the 5-dimensional term is compared to the usual 4-dimensional one. So if RC, the crossover scale, is very large, then we will basically recover general relativity. And again, in this model, you can basically express it as a scalar tensor theory in which the scalar field will mediate an additional field force. There are several reasons why we like these models so much, but it's basically because they're compatible with data. And they can be compatible because they exhibit what we call screening mechanisms. So these are ways to hide the field force in regions where we know we have very, very strong constraints that Newtonian gravity has to be correct. For instance, in the solar system, FFR gravity will screen the field force because the environmental density is very high. These models can also match the expansion history of lambda CDM, so how the acceleration of the universe is changing as a function of time, and they don't modify the speed of gravitational wave propagation. So these are all very good things that allow us to use these models and constrain data because their parameter space is not completely ruled out. But there is a downside to these two models, and is that they both need a cosmological constant to explain the accelerated expansion of the universe. So they were originally proposed to try and give a more natural explanation of why the universe expands acceleratedly, but they still need a cosmological constant. So they're not theoretically as compelling as they were once. They're still useful testbeds, so we're going to be working with them. And I'll show you some results of the n-body simulations from them and how we can use those simulations to constrain those the free parameters of these theories. So here you can see the parameter space that we've simulated. So these are 50 simulations that make up the Forge suite of simulations that are presented in this paper here. And you can see that we vary 3 cosmological parameters, omega matter, little 8, and sigma 8, together with the strength of these the strength of the field force, which is FFR naught, which tells you the amplitude of the scalar field at redshift 0. So the larger FR naught, the stronger deviations would be with respect to general relativity. And we are now working on the Entp simulations. So this is the same grid in parameter space, but here we're varying the crossover scale instead of FFR naught. Now, these are 2 very particular models. But we're working on more soon. So this is particularly enabled by faster n-body codes. These are the development of mglam. So this is a n-body code that is 100 times faster than mg-arepa. mg-arepa was used to run these bridge and forge simulations. So you can imagine how we'll be able to expand the parameter space and also explore many more gravity models in the future. For now, we're going to be looking at the 2-point statistics of the forge and bridge simulations. Here you have an example for Redshift 0.5 of how the matter power spectrum looks like for the 50 different simulations in the bridge simulations. So these are models that have different cosmological parameters and different strengths of the fit force by varying the crossover scale. You can see that it really is packed, like the difference in power spectrum is more than 3 orders of magnitude. So we're really varying a lot the parameter space. What we need now is a way to interpolate the outputs as a function of the inputs so that we can get likelihood evaluations and get a posterior on our parameters. I've been doing that with neural networks. So we have a fully connected neural network in which we input the cosmological parameters and the modified gravity parameter, and we output an estimate of the power spectrum as a function of a scale. Now we can find the optimal set of weights for this neural network by minimizing the distance between our predicted power spectrum and the one measured in n-body simulations. And it turns out that we can really get % accurate predictions with only 50 n-body simulations. I'll show you here some example of how those predictions look like. So again, this is the matter power spectrum at redshift 0.5. And here you see 4 different models, so 2 different parameter values for FFR gravity and 2 of them for NDGP as well. The error of the emulator is shown on the bottom panel. You can see that it's always within 1%. And you can also see how the different models are varying the power spectrum. So the stronger modifications would be F5 and N1. And you can see that F5 is enhancing clustering on very small scales. And these are scales that will definitely not be, so with perturbation theory, you will not be able to model those scales to 1%. You really need to run n-body simulations and perform such an emulator approach like we've done. But I told you before that we want to compare with data. We don't really measure the matter power spectrum from data, but we measure the galaxy power spectrum. But going from matter to galaxies is not something you can do in a straightforward manner because we're running dark matter-only simulations. What you can do, though, is look at the lensing power spectrum. So there was a talk previously about CL. So this is the lensing power spectrum, which is basically the weak lensing power spectrum, which is basically an integral of the matter power spectrum. So we can take the emulator that we have produced to make predictions of how the lensing spectrum should look like and use it to constrain theories of gravity. And that's what Joachim and other apps, one of our collaborators, has been doing. So I'll show you how the constraints for Euclid-like survey look like. So this is the galaxy source distribution of a Euclid-like survey as a function of redshift, and the redshift bins that we've been working with are shown in colored lines. You can see here the constraints that you could obtain with such a Euclid-like survey on the FFR naught parameter and the cosmological parameters. So we've been doing that for a simulation with a fiducial cosmology, which is FFR naught close to 10 to the minus 5. It's shown in the dashed line here. And you can see that we can recover within the blue contours the true parameter of the simulation, and that would, in that particular case, general relativity will be ruled out. But remember, this is simulations in which we put in the FR naught value. The same is true also for NTGP. So this is the constraints that we obtain on the crossover scale. And again, you can see that the error bars are very small. Ideally, that we will be able to do this with Euclid. Of course, there are things that we need to think about more, which is what is happening on those very small scales. So this is, again, done with dark matter-only simulations, but variance will play a role in real data, and we'll need to deal with that in the future. But for now, we're showing that there is a lot of constraining power on those very small scales. Now I'd like to finish by showing results from different summary statistics. So we've been looking at 2-point functions like the lensing power spectrum, but the question is whether we can look for signals that enhance that modified gravity effect. And we can do that by looking at clustering, but in an environment-dependent manner. So we could split our data into different density bins. So you're looking at the over density around spheres, And in that way, we can sort of get like clustering dependent constraints. So you can see here, the over-density values split into different quantiles. From voids, DS1 would be something equivalent to a void, to DS5, which would be something equivalent to a big cluster. And I'll just show you how it looks like. So you can basically look at clustering as a function of environment. You can see how in voids, there are underdense regions and go to overdense regions in clusters of galaxies. And yeah, that will be something exciting to do with new data to try and get better constraints on modified gravity parameters. And given that I'm running out of time, I'm just going to leave you with the conclusions and some words of caution. Be happy to take any questions. Thank you.